In this video, we are going to continue to look at Activity 2C on phase changes. And we're going to start looking at the back of this sheet where you see the word problems. And this first word problem says how much heat is released when 955 grams of steam at 100 degrees Celsius condenses into liquid water. And so in the past, we've been making calculations about the heat energy that's required to either warm up or the heat energy released when something cools down. But when a phase change is happening, you can see on our graph, our phase changes occur at our plateaus. So here and here, and then at B and D on this graph. And when a phase change is happening, there is no temperature change occurring because all of the energy being inputted is going into causing that phase change to happen. So if there's no temperature change occurring, we're not going to be able to use our equation of Q equals m times C times delta T because we are missing the change in temperature. There is no change in temperature, so our delta T would always be 0. And there's not no energy being inputted here. The energy is just going into breaking the intermolecular forces that exist between the molecules. So when we read this problem, how much heat is released when 955 grams of steam at 100 degrees Celsius condenses, it's important that the water is already at 100 degrees Celsius. It's already at the point where water will start to vaporize, where it will start, and this graph doesn't actually show vaporization, it shows condensation. But our graph for water might look something like this. So we would have the temperature starting at some point and rising up to 100 degrees Celsius. And then our water would start to vaporize, or actually in this case it is condensing, so the heat will be released. So we would have water that's above 100 degrees Celsius cooling down to 100 degrees and then starting to condense and go from the gas phase into the liquid phase. And when it's done condensing, all the water would be in the liquid phase. So all the heat energy is going to end up being released instead of absorbed like it is over here where we're going from the liquid into the gas phase. So in order to make this calculation, we're not going to use Q equals mc delta T. We're going to use our equation Q equals m times delta H. And there are two values of delta H that we use to make these calculations. We have these are enthalpy values. So we either use the enthalpy of fusion or the enthalpy of vaporization. And so we use the enthalpy of fusion, delta H of fusion, when we have a transition between solid and liquid. So melting, going from solid to liquid, or we use it when we're going from liquid to solid. And then we use delta H of vaporization when we have a transition between gas and liquid. So when we're going from gas to liquid, or we're going from liquid to gas. And so in this problem in particular, we have steam or water vapor condensing. So condensation is a transition from gas to liquid. So we will use our delta H of vaporization value here. And so these problems are actually quite simple once you know which equation to use. Our water is already 100 degrees. We don't need to release any energy to get it down to 100 degrees. So all we are trying to find here is how much energy is released on this one section of the graph. So all we need to do is Q equals m times delta H of vaporization. So let's do that real quick. So we have our value of Q is going to equal our mass, so it's 955 grams, times our delta H of vaporization, which is one of your given values on your formula sheet. It is 2260 joules per gram. And as you can see, when we multiply these two things together, our grams are going to cancel out and we'll just be left with joules, which is indeed our unit of energy. So all that we need to do here is type this into our calculator. So we have 955 times 2260, which gives us a big number, 2158300, and our units are joules. So if the problem asks you to put it in joules or in kilojoules, please make sure you do pay attention to the units the problem is asking for. But this problem only asks us how much heat, and so heat energy can be reported in joules or kilojoules or calories, or there are many different units that we use to report this. So this is a perfectly acceptable way of writing your answer right here. So the second problem here says how much energy is required to melt 27 grams of ice at 0 degrees Celsius. And so ice would be solid water, and water goes between solid and liquid, or it goes liquid to solid, at 0 degrees Celsius. So our water is already at the correct temperature to melt, so all of our energy just needs to be put into the process of melting. So all we're going to need to do is do Q equals M times delta H, and since we are going between a transition from solid to liquid, this is going to be our delta H of fusion. So we can go ahead and get these values. Q equals our mass, 27 grams, times delta H of fusion, which is on your formula sheet for liquid or for solid water, and it's 334 joules per gram. Please do note that these values are only for water. It's the delta H of fusion of water and the delta H of vaporization of water. If it's asking you to determine how much heat energy is required to melt or vaporize a different substance, the delta H value should be given in the problem. You can look up these values for a whole bunch of different substances as well if you ever need to know one. So here we have 27 grams. Grams will cancel out and we'll just be left with joules. So we just need to do 27, whoop, can't quite see that, let's move it over, times 334. And that gives us 9018. And it just says energy, so I don't need a particular unit, so I'm just going to leave this as joules, and that's my final answer. Number 3 says how much energy is necessary to boil 52 grams of water at 100 degrees Celsius. So our water is already at its boiling point. Water boils at 100 degrees Celsius, so we just need to know how much energy is required to boil off the water, to cause the water to go from the liquid phase into the gas phase. And so here we are going to use our delta H of vaporization. So we're going to do Q equals the mass of water times delta H, and since we're going liquid to gas, we use vaporization. So we Q equals 52 grams times our delta H of vaporization, which is 2260 joules per gram. So now let's type this into our calculator. We have 52 times 2260, and that gives us 117520. And of course our grams cancels out, and we are left with just joules. Box that answer as well. Our next problem says how many moles of ethanol can be melted with an input of 76 kilojoules of heat energy if the enthalpy of fusion for ethanol is 4.94 kilojoules per mole. So in this problem, it really requires that we pay a lot of attention to our units. So let's start with our equation. We know that it's giving us the enthalpy of fusion, so it gives us the delta H of fusion for ethanol, which is the substance we're dealing with here. So I'm going to put that equals 4.94, but instead of giving it in joules per gram, which is what our values of delta H for water are in, it instead gives us it to us in kilojoules per mole. So that's a little bit interesting. And then it also gives us our value of Q. So it gives us 76 kilojoules. It doesn't give it to us in joules, it gives it to us in kilojoules. So the equation we've been using, Q equals M times delta H, we obviously need to rearrange this so that we're solving for M in this case. So we're going to go ahead and do that. We'll divide by delta H on each side. And so our delta H's cancel out and we get M equals Q divided by delta H. So we can substitute these values in. M equals Q, 76 kilojoules, divided by our delta H value, 4.94 kilojoules per mole. But instead of M ending up being a value of grams, our kilojoules are going to cancel out here, and we're going to end up left with moles. And so this problem, while it looks very different from other problems we've done, we can actually follow the same process. And because of the way our units cancel out, we are already left with units of moles, which is what the problem is asking for. So this is a case where just by paying careful attention to our units, we came to the right answer in a very simple way, but initially we might have been very confused by this problem. But in the end, it turned out it really wasn't that much harder than any of the other problems we've been looking at. So we're going to end up with a number of moles here. This problem is nice and simple. So 76 divided by 4.94, and that gives us 15.38, and then our units will be in moles. So in this case, M didn't really stand for mass, it stood for moles, but we have to pay attention to units that are given in order to determine what the units on our final answer will be. And then looking at significant figures in this problem, I noticed that there are just two significant figures up here, so I'm going to go ahead and round to two significant figures. So I'm going to put my approximately sign, and this is approximately 15 moles, and I will box that answer. The next problem says how many joules are required to boil off 150 grams of water that begins at room temperature. And it tells us that room temperature is 21 degrees Celsius. So here we're still trying to boil off water. So if we are trying to have a phase change, the amount of energy required to that phase change is going to come from our Q equals M times our delta H value. But our water is not at boiling temperature. Water, we know, boils at 100 degrees Celsius, but our water is only starting out at 21 degrees Celsius. So if we look at a graph of what's happening here, we have some water. It starts out at 21 degrees Celsius, and then somehow it needs to increase its temperature up to 100 degrees Celsius before it can start to boil off and change into the gaseous phase. And so then up here we would finally have a gas, and down here we have a liquid. But we need sufficient energy to get our water all the way from this point down here, all the way up to the point where all of the water is now a gas. So we need energy to get us all the way up to 100 degrees Celsius, and then also to boil off all the water so that it is then in the gaseous phase. So we know how to get the amount of energy for this portion of the graph. That's going to come from our Q equals M times delta H. But for this portion of the graph, where we are increasing our temperature, we're going to have to figure out how much energy is required using our Q equals M times C times delta T. So we're going to have to find each of these values individually and then add them up so that we know the total amount of energy to get from here all the way to here on the graph. So we need to know how much total heat energy is needed for this whole transition here. So let's start with the easy part. Let's do Q equals M times delta H. And since we're trying to boil water, this is going to be our delta H of vaporization. So we have 150 grams of water times our 2260 joules per gram. And so that's going to get us our first number, 150 times 2260. And that gives us a nice big number. Move the paper over just a tad here. 339,000 joules, as our grams cancels out. So there's our first portion, and I'm going to go ahead and write that in over here so we don't forget it. 339,000 joules. So that's that portion of the graph. But I need to know how much energy is required for this portion of the graph. So we need to do Q equals M times C times delta T. So our value of M is still 150 grams. So that part's easy. Our value of C, remember, is our specific heat of liquid water, which is 4.186 joules per gram degree Celsius. And then our temperature change, well, we need to go from 21 degrees up to the boiling point of water. So 21 to 100. So our final temperature should be 100 degrees Celsius. And our initial temperature will be the 21 degrees Celsius that we start at. So now we just need to solve. We have all our variables in place. We need to do, well, I'm going to first do 100 minus 21. Which should give me 29, 100 minus 21, which should be 79, sorry, excuse me. So now I'm going to do 150 times 4.186 times 79 degrees. And that gives me 49604.1. And if we look at our units, grams cancels out, degrees Celsius cancels out, we're just left with joules. So that is the amount of energy required to get us up to 100 degrees, plus the amount of energy to vaporize our substance. So we just need to add these two values together. So our total value for Q equals 339,000 joules plus 49604.1 joules. So if we add those two numbers together, I'm just going to go up and select those numbers in my calculator. If I add those two things together, it gives me 388,604.1. And that is a value of joules. Then, looking at my problem, I'm only given two significant figures in each of my values. I'm going to go ahead and round this. This is approximately 3, and this 8 will round up to a 9, because 8 is larger than 5. And then, of course, I'm going to fill in zeros for all my other values. So I need 1, 2, 3, 4 zeros. 1, 2, 3, 4 zeros. And I'll put joules at the end. All right. Our last problem says how many moles of water vapor must condense to release 1467 kilojoules of heat energy. Okay, so we want moles, but we have a value of kilojoules to start, and we don't have any other information. So this value of kilojoules, it's amount of energy, so we know that must be Q. It even tells us that it's heat energy, so that's our value of Q. And then we have something condensing. And it doesn't specifically tell us this in the problem, but we're going to have to make the assumption that our water vapor is already at the condensation point. It doesn't tell us that it's not, so we're going to make that assumption here, that it's already at 100 degrees. So, we just need to know, we're looking at the equation Q equals M times delta H. And then once we have our mass of water vapor, we know how to convert that to moles, so we can do that in the end. So we have our value of Q, we have our value of delta H, and we need to rearrange this equation to solve for M. So I'm going to divide by delta H on both sides. Our delta H cancels out, and we get M equals Q divided by delta H. Coming over here, we have M equals Q, so 1467 kilojoules. Whoop, but actually we can't have kilojoules in this problem because our value of delta H is going to be in joules per gram. So we need to convert this kilojoules into joules, and we'll do that with a little dimensional analysis. Kilojoules to joules, we know that there are 1,000 base units in every kilo unit, so we need to just multiply this by 1,000. So we have 1467000 joules. So now we can substitute it into our equation. We have M equals 1467000 joules divided by our delta H of vaporization for water, which is 2260 joules per gram. Joules will cancel, and we're just going to be left with grams. So let's type this to our calculator. 1467000 divided by 2260. That gives us 649.115 grams. And of course this is grams of H2O. But we want moles of water. So here we're just going to have to do a mole conversion. We're going to take grams of H2O and convert to moles of H2O. Oxygen is 16 grams per mole, and each hydrogen is 1 gram per mole, so water is 18 grams per 1 mole. So we take our value, divide by 18, and that gives us a number of moles of water. So this ends up being 36 moles of H2O.